And with that, I think we can move to start. So with that, from my end, again, welcome to the first SentroConnect live webinar. It's great to have you all joining here. We'll have a number of presentations, 2 in total, from the Sentronic team. And with that, we'll start in a moment. For the time being, I do want to quickly comment on the poll. For that, I will now end the poll to be sure. Good. And you should all see the results already. So as we can see, we do have quite a number of continents present. We have a larger, or the majority from Europe, but also from North America and South America, as well as from Asia. I think that does pretty much fit the registration, Sebastian, from what I can tell. The SentroConnect Live is targeted not only as experienced, but especially at novice industry members for PAT. Therefore, I'm quite happy about the results. So we do have, of course, a number of SMEs, all in PAT pros and Chemometrics, but we also do have a representative number of basic experience or not yet PAT practitioners. So especially those who might be interested at learning the basics of PAT here, specifically NIR and the analysis. So with that, I'm quite happy to see that on the result, which fits the target audience as well. And with that now, it's my pleasure to introduce the team. By the way, my name is Hubertus Rehbaum. I will be just moderating today, not presenting, but instead we do have 2 presentations. However, before we jump into the presentation, we want to get to know the team from Sentronic, both in Germany and US. And with that, I will give the word to Uwe to start with an introduction and then do a round table.
Okay, thank you, Hubertus. Thank you very much also for organizing and helping us to set the first SentroConnect live up. Great and good experience to work with you, as always. So I'm Uwe, co-founder of Sentronic, and since 1993 with Sentronic, I came from Technical University in Dresden with an electrical engineering background, and my work life is Sentronic since then.
Great. Then we'll go on to Owen.
Hi, I'm Owen Rehrauer. I'm the president of Sentronic US Corp. I've been with the company since its inception in 2022, although I've been a global Sentronic partner since 2019.
Right. Sebastian?
Hello, everyone. My name is Sebastian Zawinski. I'm with Sentronic since 2000, and I'm key account manager at Sentronic GmbH in Dresden.
And last but not least, Adam.
Hi, everyone. My name's Adam Rish. I've been with Sentronic US as a scientist since last year. So about a year and a half with the company.
Great. So the focus of today will be both Owen and Adam. Today's first webinar provides introduction to PAT and data analytics. So especially from the US team, those 2 will be presenting. Of course, we are looking forward to your questions. So any questions that you have, you can already provide or enter in the Q&A system of the webinar. However, we will only move on to answer the questions after both presentations have been heard, just that we will allow to have the full presentation and then sufficient time for answering all of the open questions. The first presentation will be by Owen to investigate and understand NIR PAT for bin blending. So that is focusing primarily on the technical hardware. Afterwards, Adam will speak about Chemometrics with NIR spectra, both providing an introduction. So really this webinar is also intended for novice PAT practitioners and those who want to learn about this. And with that, I think we can start now and move on to Owen. I will, with that, ask Owen to start sharing his screen and look forward to your presentation.
I apologize, Hubertus. We seem to be having some technical difficulties. I'm unable to share my screen.
Yeah, that was me. I should, of course. Now you should be able to do that.
Fantastic. Thank you.
You know, if it's technical, I'm usually at fault.
Shucks. Well, apologies for the technical difficulties here, folks. That having been said, thank you all for joining the inaugural SentroConnect presentation. As Hubertus mentioned, my name is Owen Rehrauer, and today I'll be presenting to you a basic overview of PAT and NIR PAT with a focus on bin blending applications for pharmaceutical analysis. So we're going to start with some real basics. What is PAT? Why people might want to use PAT, particularly in a pharmaceutical application. We'll cover some of the fundamentals of NIR PAT from an instrumentation and application perspective, and then spend some time on solutions and some technical aspects of bin blending for pharmaceutical PAT. What is PAT? I've got the definition that the FDA has put in their PAT guidance up on the slide. I'm not going to read off the slide, but I want to highlight, and I've done this via the bolding in the text here, that this is timely measurements made, for example, during a process that are tied to critical quality attributes that help ensure final product quality. That differentiates PAT from other soft sensor measurements. What's motivating the use of PAT? We've used conventional laboratory analysis for many years successfully, and people may be asking why change for something that's been working well. Well, there's a long time between the actual processing in pharmaceutical manufacturing and laboratory analysis, and that unfortunately prevents the ability of making interventions if a process is undergoing a change from its target performance. The cost of losing a batch as a result of this can be quite high, so there's some business incentives to want to use PAT to avoid this eventuality. Sampling material can also be challenging. If you're taking something like core tablets from a tablet press, that's quite easy. But thief sampling and bin blending, for example, is known to be prone to sampling errors and problems that then create investigations, deviations, and just generally some headaches. So if we can avoid that, there's also some good reasons to do that as well. In the US context, the FDA also will, in some cases, give advanced manufacturing designation to control strategies that include PAT. So there can be some regulatory advantages in terms of speed of filing and approval of a drug via the use of PAT. And last but not least, these measurements can be useful in process understanding and optimization, particularly during product development. So what are the benefits? Well, there are going to be answers to all of those, but there's a few others I want to highlight as well. So yes, of course, PAT can get you real-time process insights. That can be used as a guardrail to help avoid any failures of batches, but it can also be useful for making interventions or getting some understanding of the process itself. When implemented in an inline or online way, there's no sampling required, so we can get away from things like thief sampling. In addition to the benefits and motivations I mentioned before, I do want to highlight that PAT can be useful in implementing a quality by design or QBD approach and can be used to support real-time release testing. QBD is something that I find a lot of novice PAT users have some confusion on. In fact, some people think QBD and PAT are synonymous. So I do want to just cover what QBD is and how PAT interacts with it. When we look at conventional manufacturing, how we've done pharmaceutical manufacturing for quite some time, we have to acknowledge that there's some variability in the inputs to our process, whether that's material variability or environmental variability, etc. Historically, we've tended to use fixed process parameters to run a process, so a constant speed, a constant compression force, etc. And from that process, we'll get a variable output. We test at the end, and we hope that we're within an acceptable range of quality. This, of course, is not ideal because occasionally we will not be within the range we would like for quality, and we have to reject some material from use. QBD manufacturing, in contrast, of course, starts with the variable inputs. However, we use a design space of acceptable ranges of processing parameters. So rather than having a fixed number for speed or compression, we, during development, would qualify an acceptable range of speeds, compression forces, that we can use to get acceptable product quality over the range of variable inputs to our process. And then we adjust our processing parameters within our design space to help ensure consistent product quality. By using PAT, we can make measurements to best understand where in our design space we are and where we might want to set our processing parameters to help ensure that high product quality. It's often said that PAT enables a QBD approach. This is how PAT does this. I just wanted to cover that basic point because I do see a lot of questions on it and hopefully preempt those from the chat. That's an overview of some of the fundamentals of PAT, but let's talk about NIR PAT in particular. Here, I have a cartoon version of an NIR spectrometer and associated probe system. I want to cover just some basics of the instrumentation so people have an understanding of what's going on under the hood inside the PAT boxes that you'll actually see on the floor. In its most basic form, NIR spectroscopy is an absorbance spectroscopy. Oftentimes in the pharmaceutical or food contexts, we'll use what's called diffuse reflectance spectroscopy, where light's shown on a sample, and we look at the light that's back reflected from the sample itself. This is in contrast to transmission spectroscopy, where we'd actually shine light through a sample. That can be challenging with things like powders and tablets, given the thicknesses we typically work with. So light is going to come from some broad light source. Usually it's transmitted through a fiber optic cable into something like a process probe or to a process window. We measure some light, which comes back from that sample, and we transmit it to a spectrometer. Sentronic tends to prefer using diode array spectrometers. So here I've shown a cartoon diagram of what that looks like, where light is transmitted to a grating. That grating separates the light based upon its wavelength, and then it's detected on an array. The output of the detected spectra is then transmitted to a computer where it's saved to file. This is how the magic happens inside the box. I do want to cover a little bit about diffuse reflection. As mentioned before, we're looking at light that's back reflected from the sample. We will typically, at the beginning of an experiment or the beginning of a day, measure what's called a 99% standard. Some people may call this a background, to understand how much light can be reflected when almost all, 99% of the light is back reflected. This helps us get an absorbance calculation. When we measure this in powders, though, I want to highlight that the light is going to penetrate somewhat into the sample, getting deeper and deeper in, depending on some of the sample qualities. These can differ based upon whether the sample is more or less dense, or its particle size distribution has changed. This affects the functional path length, how deep the light goes in and comes back. And as a result, it's often said that diffuse reflected spectrometry includes information about chemical as well as physical sample information. I believe Adam will talk about this later because for some analyses, we want to avoid information about the physical attributes of our sample. In others, we may care about that quite a bit and use different analysis methods to highlight that information. So what are we looking at when we look at an NIR spectra? We are looking at harmonics and overtones of the mid-IR spectra. Here I've shown the near-infrared spectral range and the chemical moieties where these different functional groups will have absorbances. Unfortunately, because we're looking at harmonics and overtones, it can be a little bit difficult to do something like structural elucidation from the NIR spectra of a pure sample alone. We instead get something that can be thought of more like a chemical fingerprint. Here, I've shown the NIR spectra over a range of water. I do want to highlight for powders that there's a wavelength-dependent depth of penetration. How far light goes into a sample can depend on wavelength. And I also want to highlight in general, as we move from 750 to 2500, the intensity of absorbance bands tends to increase for some basic physical reasons. Here, I will also highlight for the system that we're going to talk mostly about today, the spectral range where we're looking. Our systems tend to cover the majority of this range. We don't tend to cover all of it as a Fourier transform system might. This is a trade-off we make to ensure that we have the most robustness possible for a process area, and so we're robust to things like vibration and temperature changes. I also want to highlight that our systems cover the range of 1700 to 1900, which can be very important in a lot of pharmaceutical applications, as this is where many important peaks from things like lubricants can occur. What might someone use NIR PAT in a pharmaceutical application for? Well, common applications include monitoring blending uniformity during mixing, whether that's bin blending, as we'll discuss more today, or for continuous blending and things like continuous manufacturing applications. NIR PAT is also routinely used for content uniformity. This can take the form of, for example, transmission NIR measurements of tablets. NIR is commonly used for material ID, so looking at raw materials before they're placed in the process area to confirm that when we think we have microcrystalline cellulose, we really do. And of course, NIR is commonly used for drying applications. In pharmaceutical applications, this could be something like monitoring fluid bed drying. Sentronic provides a number of solutions for these different applications. Here I've highlighted different common unit operations in pharmaceutical manufacturing, and just wanted to quickly mention that we have solutions for a variety of these. The orange checkmark, which you'll see at the bottom right-hand side, is our bin blending application solutions. We're going to be talking about the system on the left, the smaller SentroPat DA, although I will note that since 2005, we have been providing solutions for bin blending. The larger SentroPat BU2 is a venerable system that's been used for quite some time, whether it's in development or in commercial applications. Last but not least, we do have a newcomer to our offerings, the SentroPat ID, which can be shown here, which can be used for identification of raw materials. You should be hearing more about this product from us shortly. So you might be asking, why would someone want to use NIR PAT for bin blending? Well, we can avoid thief sampling, which tends to be a very desirable thing for a lot of people that do bin blending in pharmaceutical applications. We can also provide some information about the potency of the final blend, which can be useful for understanding the success or failure of following tableting. It supports some data process optimization. So if we are interested in optimizing how many revolutions we execute, we might take a guess that we need to do 300 or 400 just a priori to make sure we really get to blending, and then find out via NIR measurement that actually after 150 revolutions, we're actually blended. If we're making multiple batches per day, shaving off 80% of your total blend time can be a big win from a product efficiency standpoint. Last but not least, the NIR PAT can be useful in troubleshooting root causes of unusual product behavior. We can be sensitive to things like segregation and agglomeration in ways that may even be difficult to find from thief sampling. As a result, there's a lot of measurement benefits to using NIR PAT, and we're seeing more and more pharmaceutical companies get interested in using this for bin blending. So how does this all work? You're going to have to I apologize for my poor artistic skills, but this is my graphical representation of the bin blending process. Here in the middle of the circle with arrows around it, you can see my representation of a bin with one of our SentroPat DA systems stuck to it. We'll put the system onto the bin, and then we'll start rotating the bin around on its rotating. As we move around, we will come to a predefined angle, at which point the NIR PAT system will make a measurement. We use an internal 3-axis accelerometer to detect the angle of the system and trigger a measurement at a fixed angle. We do this because gravity will force powder to a process window we've installed on our bin that connects to the NIR PAT system. And when powder's in front of the window, that's an ideal time to make a measurement. Suffice to say, if there's no sample in front of the window, we're not going to get a lot of process information about this. We have found that trying to do this via timed measurements as opposed to actually using the angle itself can be tricky for synchronization, particularly for bin blenders that actually will change the direction of rotation. Timing can be quite difficult there. By using the angle, we seem to get the most robust sampling of our material. So we're going to make a measurement as we're going around, and then the bin blender is going to continue to rotate around again and again and again, collecting one NIR PAT measurement per rotation. When we're done, we'll stop our bin blender, we'll stop our PAT measurement, we'll take our system off, and then we'll go to analyze the data. How do we do that? Well, Adam will cover that in just a few minutes. This is all well and good, but let's actually take a look at this on a system itself. So here I have one of our systems installed in our unit operation simulator, the Centro Blender. We have a glass vial here so we can see quite easily when measurements are made during the rotation process. So we're going to start rotating the Centro Blender, and you will see when powder is in front of the window, we turn the light on, which is indicative of a measurement, and we turn it off when powder is not there. So on, off, on, off, and again and again and again. So what does that process window look like? Here is a picture of a modified bin lid, which tends to be the most common way NIR PAT is connected to a bin for blending. We have, of course, also modified the bins themselves, but by modifying the lid, we can use that what was commonly called a PAT lid with multiple blenders. Multiple bins, which can be quite useful if we're comparing or trying to scale up different bin sizes. On the other side of this will be a flange, and that flange can be used to, using a C-clamp, attach the SentroPat DA. So speaking of the SentroPat DA, this is our latest and greatest solution for bin blending. It covers a wide range of the NIR spectrum, allowing us to be sensitive to most APIs, excipients, and lubricants. It has internal intensity and wavelength standards, which can be quite handy because you can use these for system suitability testing, making sure the system's in good health, without having to have operators bring the standards onto the process floor. For bin blending applications, we want to, if we possible, be completely wireless. It would be a bit challenging to connect wires to a moving bin, so this system is fully battery powered with a long battery lifetime, as well as fully Wi-Fi enabled, so we can communicate with a laptop or local server without the need to connect communication cables to the system. It's also quite lightweight, weighs about 5 pounds, and it's small enough to fit on development blenders like V blenders, but also still is quite useful on commercial scale blenders as well. In terms of control of the system, we'll touch on this very, very briefly, but we have an internal set of software called SentroSuite GMP, which can be used for control and a collection of measurements on all our systems, including the SentroPat DA. This software can also be used to execute, common validation tests. These tests include tests tied to the USP 1856 as well as EP 2.2.40 test requirements, as well as some vendor specifications as well. And the software is, of course, compliant with the relevant versions of 21 CFR Part 11, which is quite important for our pharmaceutical customers. In addition to this software, we also do have the ability to control our system using some common control softwares. Things like Siemens SciPat, SciY, SyntaQ, etc. If you have questions about this, feel free to reach out and we can talk about what we're compatible with. So what are some common integration questions that we get? We get a question a lot, can the system be controlled via OPC communication for integration with blender control software? The reason for this question is commonly because people would like to use an endpoint detection determination made via the PAT data. Basically, once we get to a certain point, can we have the NIR tell the blender to stop blending? The short answer is yes, we can. If you have additional questions, feel free to reach out. There's a question often around what flange sizes that our systems are compatible with. Commonly, it's 2-inch, 4-inch, and 6-inch diameter flanges. These allow us to be compatible with the Sentronic historic PAT solutions for bin blending, the SentroPat BU2, as well as several other vendor solutions. Again, if you have questions, feel free to reach out. And we, of course, always get questions. It's a real common PAT one. If we take laboratory analytical systems, bring them to the process floor, are they going to be rugged enough? We have spent a lot of time ensuring our systems are rugged enough. However, I would recommend avoid doing something like this. These are tough, but try not to hit them with a forklift if you can. So let's put it all together. We've mentioned this is complicated, all the different steps involved, but I think you'll see in the attached video where I believe one of the members from the Sentronic team here is going to be actually showing you how easy it is to collect NIR PAT data. Oh, here we are. Sorry about that. So you can see here, Sebastian is attaching the system to its PAT lid. We're going to then connect the bin to our blending arm. Slowly move up. We're rotating around, collecting our blender revolutions. You can see our system there. And from that, we're going to get spectra in SentroSuite. That's as easy as it can be. With that, I will say thank you for everyone's time, but more importantly, I want to pass it over to Adam for his portion of the presentation. Thank you for attending, and I look forward to your questions shortly.
Perfect. Thank you, Owen, for the presentation. A brief reminder to everyone, of course, you can already put questions now. Note that the questions, you put them down in the Q&A system, will not be visible to everyone, and I would like to encourage you The webinar is meant to answer any questions you have. There are no basic questions not allowed, so feel free to share them. And you can also ask anonymously if you prefer this. With that, we will move on now. We have now Adam Rish, who will speak to us about chemometrics. With that, it's a logical continuation of the topic. So we'll look at how we analyze the signal that has been acquired using an NIR system. With that, Adam, I'll let you share and look forward to your presentation.
Great. Thank you, Hubertus, for that introduction. Just give me a moment to share my screen here. All right. So today, as it was indicated, I'll be speaking a little bit about the basics of chemometrics. So as Owen showed, we want to convert our NIR spectra into process information. But how do we do that? That's where chemometrics comes in, which is basically the application of statistics to interpret our chemical spectral information. So when we think about chemometrics, we have a couple choices we can make on what kind of techniques we want to use. And to help us sort out what would work best, we want to ask two questions. What information do I have, and what information do I want? So if starting from the left-hand side, if you have just spectra, this is where we have no ability to correlate that information with reference values, something like API concentration, and we would call that an unsupervised analysis. And these types of analyses are ideal for data exploration or process understanding. But if we do have reference values that we can take advantage of from a separate reference technique, such as HPLC, we can correlate that spectral data with those results directly, and we would call this supervised analysis. And this is ideal when we want to do things like data prediction and classification and collect process information. So we've picked our analysis type. What kind of information do we actually want? So there's qualitative information, and this might look like, is the blending complete, endpoint detection, or does the sample look like other samples? For quantitative applications, how much API is in this blend sample, and how much lubricant is in this blend sample? Those are common quantitative applications. But before we actually get to the chemometric analysis, we might want to do some digital processing of our spectra. This is called spectral pre-processing. And there's several reasons we would want to do this that are beneficial to our chemometric analysis. Here, we might want to emphasize specific spectral features related to the target of the analysis. Naturally, a choice would be API. And for that, we're going to want to take a derivative to make an API peak sharper and less overlap with our competing excipient signals. And also, as Owen mentioned, we get both chemical and physical information in our NIR spectra. So being able to minimize the impact of that physical information is really useful, and that can be achieved by doing that pre-processing. Some of the standard pre-processings you might see are standard normal variate transformation, SNV, Savitsky-Golay filter with derivative, and I'll just be calling that SAV-GOL, and then wavelength selection, and we'll cover each of those in just a moment. And those spectral preprocessings I just mentioned, those are widely available in any kind of chemometric software package, so very easy to apply. So SNV, and you can see the transformation here, is on the left-hand side. With the raw spectra, there's different baselines of spectra. But when we apply the SNV, that collapses those baselines together so we can actually see the changing API content between 16 and 1700. And that's exactly what SNV does, is it helps us account for some of those physical characteristics in the NIR spectra, physical characteristics manifesting from things like bulk powder density changes or changes in the particle size distribution. And that is very ideal for our blending applications. For Savitsky-Golay filter, this is a smoothing, so this is really useful for removing noise from the spectrum. Taking a derivative can also assist with removing some of those physical effects that manifest in the baseline. And taking the derivative also highlights the chemical features of the spectrum rather than just the baseline changes. And again, focusing on that peak between 1600 and 1700, which is our API peak, you can see how much more that chemical peak is emphasized after we take the derivative of the spectrum. For wavelength selection, this is a very common practice, especially trimming the edges of the spectra where we might be higher noise. So we remove noisy regions. We can remove interfering or non-relevant signals from the spectra. And particularly, depending on the type of analysis, we can just focus on the regions that are relevant to our target analytes, such as the API. So we're going to be covering a couple different chemometric techniques, focusing on ones that are relevant to blending. So simple methods, which is that you can certainly use, but chemometric techniques uses multiple regions of the spectrum and have much more data richness in the application for bin blending. So we're going to be talking briefly about each of those 5 techniques that I've listed there. So moving block standard deviation looks at the standard deviation of a block of spectral data using a moving window. And it's basically measuring how does my spectra change over time. And if we're trying to do blend endpoint detection, when the spectra has stopped changing significantly, and we typically define that according to a tolerance limit, which you can see in the plot on the bottom there, that's when we say our blending is done. And one of the advantages of moving block standard deviation is that it does not require a formal calibration. And this is something that we sometimes refer to as a lean chemometric method. And then, of course, application for blending is blend endpoint detection. And so just to visualize, you can see we've just collected our first, using a block size of 3 spectra, we've collected our first standard deviation. And as the block slides along over time, we collect a new data point, looking and measuring how those spectra change. A related method is something called the moving block F-test that compares the variance between 2 separate blocks of spectra, which you can see there represented by 2 windows. And the advantage of this technique is that there is an acceptance limit built into the actual method, a tolerance limit via statistics, which saves you some effort in terms of having to define your tolerance limit. And again, this method doesn't require calibration, and it's very similar applications to moving block standard deviation. And you can see, as it moves over time, the variance comparison, which is represented there by the fx variable, is tracked over time. So moving on from the moving blocks methods, I want to briefly mention iterative optimization technology algorithms. These specifically use pure component spectra of the raw materials to convert the NIR spectra into what we call relative concentrations for each material. And you can see how that's represented there. We take our pure components and we're able to track the individual trends of each ingredient in our blend over time. And again, this is considered a lean chemometric technique, which is very advantageous for specific applications and can be applied in a qualitative or quantitative capacity. And so as such, it can be used for just general blend endpoint detection, but also blend potency assessment if you're looking to find out what your final API concentration is. Another popular method is principal component analysis, PCA, which takes the original NIR spectra and condenses it from hundreds of variables down into just a few small variables, which we refer to as scores. And these scores are directly related to the variance of the spectra. And so you can see there on the right-hand side, converting our raw spectra into PCA scores. And we can look at the trend of those scores over time to get an idea of how our blend is progressing. We can also plot those in 2 dimensions, plotting each score against the other score, and see a trajectory over time as well. A key consideration with using PCA models is that they do require a set of calibration spectra, and make sure when you're applying spectral preprocessing that you're doing this prior to running your PCA analysis. But the advantage is once we actually have a calibrated PCA model, we can investigate both how the original samples relate to one another, as well as new samples that can be placed into that PCA model and understand how they relate to the original calibration set. And applications for PCA is data exploration, since it's considered an unsupervised method, and also for blend endpoint detection. And then the final technique we're going to comment on today is partial least squares PLS regression. And this is where we're directly correlating our NIR spectra with reference values of process information. Of course, for pharmaceuticals, that would be your API potency. And you can see what the reference, what our expected value would be versus our predicted from the actual PLS model. And you can see how those correlate quite nicely in the plot on the bottom there. And so just like PCA, we need a calibration set, and then we also need to actually know what that calibration set of spectra, what the true value of the API content might be, which you would get from something like HPLC. Of course, spectral preprocessing is essential for PLS modeling, but once you actually have the calibrated model, you can use any kind of new spectra that you obtain to predict what the actual API content might be from that sample. And so applications for PLS, predicting API potency of the sample, you can also use it for other components of your system, such as lubricant, and then of course, blend endpoint detection. So we've talked about a number of techniques. Which one is best for you? And here are some good questions to ask your team as you're deciding which one you should use. What is the goal of your analysis? What process information do you want to generate from the NIR spectra? Spectral preprocessing. What spectral preprocessing should you use to get information from the NIR spectra? Are you interested in chemical or are you interested in physical information? Calibration burden. How do the time, material, and financial costs to develop and calibrate the selected chemometric technique align with project goals and timelines? Level of expertise. Do you have the necessary expertise and chemometric software available to properly develop and implement a given chemometric technique? Validation and regulatory requirements. What are the expectations from regulatory authorities in terms of method validation and maintenance? So, to just briefly summarize the techniques we discussed, moving block standard deviation, we're looking at the change in the standard deviation over time. Moving block F-test, we're looking at the changes in variance between two blocks over time. IoT, we're predicting relative concentrations for individual components in the system in the NIR that are represented in the NIR spectra. Principal component analysis, we're simplifying that NIR spectra down into just a few small number of variables. In PLS, we're correlating the NIR spectra with reference values to enable prediction of future process information. And so you can see how chemometrics ties that NIR spectra nicely together with obtaining process information. So here's just a summary table, and you can see how each of the algorithms we talked about relates to qualitative versus quantitative analysis, if there's calibration required. Of course, all of them can be used for blend endpoint detection, which is one of the critical quality attributes for blending. Blend potency assessment, you can do that with IoT and PLS. And also advantageously, if you're using our software, we offer moving block standard deviation and moving block F-test as part of our SentroSuite software, which I'm going to demonstrate shortly here. And then also IoT, it will be soon available to, and then as Owen mentioned, we can integrate with a number of partner softwares to allow you to also do PCA and PLS. So this video briefly shows how we can implement moving block standard deviation and moving block F-test into SentroSuite. So here I'm going to set up specifically analyses, and we're going to just call it SentroConnect. And I want to apply some pretreatments or pre-processing. So here I'm applying SNV. And we're doing that over a specific wavelength range. And then we have SAV goal, and we're going to call this SAV goal 2D for second derivative. And we're entering our derivative order here and the window size, which just tells you how many wavelengths you want to actually apply the smoothing over. So first, we're going to set up the moving block standard deviation and name it appropriately. You can see the wavelength ranges we set there, and we've set our block size to 5 spectra. Applying our pre-processing. And now we can set up our moving f-test, which is listed here as f-test monitor. Just putting the name in. And applying our pre-processing treatments, of course, and then setting our block size to 5. And of course, as you might remember, there's 2 blocks, so it's actually a total number of spectra that we're looking at one time of 10. And then we're going to go over to display, and this is just to make sure when we're running our spectral collection that we're actually seeing the moving block standard deviation and moving block f-test show up. And then we're going to proceed to take a measurement. And you'll be able to see the change of the spectra over time. So we're setting our analysis to SentroConnect, and we're going to start our measurement. And you'll see the spectra change over time as things start to blend together. And then once 5 spectra pass, we'll start to see the moving block standard deviation. And then because we have 10 spectra we need to account for, the moving block f-test, we'll start to see a trend emerge for that once we've hit 10 spectra collected. And you can see that trend appear. And the stabilization of the trends at around 144610 is how we're going to know that our endpoint has been reached. So that's it for that demo. And with that, I will conclude my talk. Thank you very much, and I look forward to hearing any additional questions you might have. Thank you.
Thank you, Adam. That was a very interesting talk, very basic at some points, which I think is good in the intention to get everyone on board. And I may say that as in this talk, we did get a number or quite a few more questions. That's a quite good thing. I will ask now everyone to switch on the video again from Sentronic so that we can move on towards the Q&A session. For those who still might have now get questions coming in, of course, feel free to still post them via the Q&A function within the webinar. However, we will start already with the first questions. And as said, there were a number coming in during your talk. Adam, I'll start with that. The first question is around the quantitative versus the qualitative approach and the identification of endpoint. I suggest maybe can you rephrase the quantitative versus the qualitative approach and how endpoint criteria fits into the two concepts?
Sure, certainly.
As a more basic explanation, maybe also.
Sure, absolutely. So when we say qualitative, that's more of what we would consider just a description. So you can almost, at the most basic, it's yes or no. So for a blend endpoint, is our blending done? And at the point where we would say, when we transition from no blending is not done to blending is done, that would be what we would call our blend endpoint detection. So that's a very basic kind of qualitative assessment. Is blending done? Compare that with quantitative, where your blend endpoint is based on an actual numerical value. So for example, that would be your API content. So you're going to see that change over the course of the blend as that API powder gets incorporated with the other excipient powders. And at the point where you actually reach your concentration of API and that concentration is actually stable, according to, for example, your PLS model, as calculated, as observed by the NIR spectra, at that point, when you have a stable API concentration at the concentration that you're targeting or within the acceptance criteria of that concentration, we would say that's a quantitative determination of the blend endpoint. In terms of which one would be preferred, that kind of comes down to what is the personal needs of your application. And that's about the best recommendation I can give. Qualitative has its advantages in terms of being easier to develop and deploy. Quantitative gives you a lot more confidence in the quality of your actual product.
Perfect. As a follow-up, another question that fits to it as we speak about the endpoint criteria, can you elaborate how we establish an endpoint criteria? For instance, how many batches of data do need to be recorded? What is your experience? I might add here, of course, this is something that you as a supplier is not always easy, or for you as a supplier, it's not always easy to ask. So maybe word from my end, the comment, whatever you provide is a recommendation. It's not something that can automatically be approved by the authorities. But maybe you can comment on your experience on the number of batches and how such a development of an endpoint criteria typically is happening.
Yeah, so of course, it's going to depend on your actual product, what you need to meet and justify. The approach of your analysis is also going to play a big part in that. So for moving block standard deviation, we would determine the endpoint as occurring once you're below that tolerance threshold, and that establishing that tolerance threshold is going to be dependent on a lot of empirical analysis, where you're running actual experiments and seeing how long the blend takes, and then how long is acceptable to your procedure that you're waiting for that moving block standard deviation to be stable below that tolerance threshold. This is where the moving F-test has a lot of advantages because it establishes that threshold statistically rather than based on experimental data. In terms of what I would recommend, again, it's going to depend on, it's more product dependent. And also just part of it is also just operator experience. Typically, when you're doing these kinds of analysis, you are doing the process development and you already have at that point developed an expectation for when the blend might be done. So that is kind of what I would recommend. I personally don't have a ton of experience in doing the development directly. So I mean, I would certainly appreciate Hubertus or somebody who has more experience like Owen also providing kind of some feedback on what they would recommend.
Yeah, I'll jump into that one. In general, your NIR PAT is being used to validate that your blend is done. The way that you know your blend is done is going to be from an analytical method, for example, thief sampling of material and analyzing it in a laboratory. Your method validation would be correlating that the NIR PAT output aligns with your laboratory empirical method. That would be the validation of your method. That's how you know you can trust the results of it. That tends to be the method that people use to, for example, have confidence in their threshold for something like a moving block standard deviation analysis. For a quantitative approach, it becomes, in my opinion, a bit more clear, although I would caution when you're looking at a quantitative output, you are looking commonly only at the prediction of something like API potency. That may not be telling you the full story for your blend. For example, you might see that when you're looking at the lubrication step, your API potency doesn't change very much. If you've added, for example, 0.5% of lubricant to your mix, you may care quite a bit though about the lubricant percent. So I think the answer is it depends. It's complicated, but in general, you want to correlate your NIR output to some reference method to have the highest degree of confidence for it if you're progressing this towards a commercial application.
Right. Yeah, it depends is something that quite often comes up. I know this, but I think it's the recommendation that here counts. I'd like to proceed with a question that comes back more to the equipment and there more the software. We had the question, what about data integrity? How does it work, especially with SentroSuite, using it either in non-GMP or GMP environments? How is the software installed or operated? And is it possible to separate between non-GMP and GMP data acquisitions? I'm not sure who's best to answer this, maybe Owen or...
Yeah, I can field that one. So I'll start at the end and then I'll work back from there. In terms of GMP versus non-GMP, We do actually have GMP and non-GMP versions of our software. We tend to only install the GMP version just because that tends to be something that is changed during a process development in pharma, and the software is a bit binary and nobody wants to requalify equipment. So then it becomes more how you use the software and how you parameterize the software, how hard you lock things down. That is somewhat configurable. We tend to see more lockdown as we move more towards a commercial space. And I apologize, Hubertus. Can you just give me the front end of that question again, just to make sure I'm answering what's being asked?
You answered already a major part of the question. The last one was the data integrity in general. I suggest we don't look now at the audit trail, but rather like how data integrity of storing and protecting the acquired data, how that happens.
Yeah, good question. So at the most basic level, when customers are just collecting data in our analyzer management software, SentroSuite, we control via Windows services the integrity of the data using a service called Sentronic File Security, which prevents users from deleting or modifying data as long as that service is running. It is common that users will have different levels of permission. One of those permission levels is that non-SMEs or non-admins cannot turn on and off the software. So somebody can't get around that. At a higher level, though, commonly, particularly as we move to commercial, people may want to use something like a PAT data historian or other software to control the system. That may include, for example, having the data not saved locally, but only into a PAT database. Common software there might be something like SciY Synteq, Siemens SciPat, CAX software group ProAxis. Those softwares then have their own set of data integrity. I don't want to speak on their behalf, but I would say it's a commonly accepted managed way to handle it.
All right. There's a related question around the use of historians. If Sentronic equipment and SentroSuite can be used to also forward the spectral data, not just the pure results, to a PAT historian, I'll take that question actually. The answer is technically yes. The software does have an inbuilt OPC server. With that, it's possible, of course, to configure any standard PAT historian that does support OPC or works as an OPC client. So whether you're looking at Viva or formerly OSIsoft Pi, or if you're looking at IP21, this technically is possible. However, the bigger challenge here is whether or not the historian is able to process the amount of data. Keep in mind that a spectrum, like a standard spectrum, will have more than 1,000 wavelength, so individual points. As such, if you're running a blending with, let's say, one rotation within 8 or 10 seconds, you'll have a number of values coming in, which most PAT historians are not very happy about, or especially if you want to analyze this. As a result, from experience, I can say that it's technically possible. If it's something that you want to do, is on a, or might be on a different piece of paper. We do have another technical question that comes to the use of the SentroPAT DA in this case within an OEB4 environment. So the more specifically, how can it be used when operated within the glove box on an isolator? So is the Wi-Fi signal strong enough to also be received outside the isolator? And as a logical follow-up, what about cleaning afterwards? What kind of cleaning solutions or detergents can be used? And is the system able to withstand classical cleaning detergents so it's not being affected? Anyone wants to take that question? I might answer at least on the first part of the wireless transmission. In the end, I'd say it depends a bit on the isolator glove box. If you are creating a Faraday cage, then of course you have a problem. There are ways then, of course, to integrate the Wi-Fi antenna, and I'm not talking about the Wi-Fi antenna inside the SentroPAT, but the receiving one inside the isolator glove box, if that works. If the glove box does not act like a Faraday cage, then of course the Wi-Fi signal will be able to pass through. There are simple tests to do this. It's not really rocket science to confirm or not, or to confirm or see if the Wi-Fi signal can get through the isolator. What about the detergents? Owen, Sebastian, any one of you?
Yeah, I can handle that one. I'll handle this in two parts. The first one, just going right for it. We routinely have customers using some pretty common cleaning solutions on our systems, whether that's isopropanol or some dilute detergents. We've seen success there. It is pretty robust to that. I will note that we do have an IP rating. We are not intended for spray down. But the caveat I'll give here too is the SentroPAT DA itself is actually not in product contact. Of course, that doesn't mean that powder is not going to get on it. Those of us who've worked in pharmaceutical environments know that that's not always the case. But from a product contact standpoint, remember this is behind a sapphire window, so we should be minimizing the amount of material in contact with the actual analyzer itself. The sapphire window is made of industrial sapphire. That is pretty dang robust to isopropanol, mini detergents. I would caution if we're using detergents, particularly on the optical components, just to make sure that we're not having detergents that leave a residue. Also, when we clean the SentroPAT DA itself, I would caution against spraying detergent heavily near the actual tip of where the light is coming out of the SentroPAT DA. We just don't want to damage that anti-reflective coating or leave a residue on the actual optical components. But the chassis itself is pretty robust.
Good. We're not at the end, but I'd like to briefly announce that obviously because of the number of questions, we'll not be able to answer all of them. However, first of all, the 2 presentations today will be uploaded to the Sentronic YouTube channel at a later point, probably within the next couple of days. And further on, there is the intention to host a follow-up meeting, more of a meeting style, for which you can receive an invite, where also all the remaining questions, of course, will be addressed. I think based on looking at the time, we still will be able to at least answer here in live, maybe 2 questions, maybe 3, but none of the questions shall remain unanswered. We will keep them and include them in the follow-up meeting that's going to be announced probably within the next 2 weeks. With that, let me just look at another questions. We did get a number of questions around the IoT approach and also generally moving block standard deviation. So that's something, again, more for Adam. First of all, Adam, the quick question, is the IoT monitoring approach for API effective for API under 2 to 4 or 2 to 4%, so very low concentration API? Can you say something around that?
Yeah, so there's been reported success of using it for around 5%. But of course, as the lower concentration you go, the less that particular API is going to contribute to your overall signal, and it might be hard to actually identify that in the analysis. But we do have, at least not API, but for mag sterate, it's been successfully detected by IoT in a qualitative application at around 1% weight per weight. So with a proper analysis, you might be able to do it. A lot, again, it's going to depend a lot on a couple other factors. What are the excipients in the actual system? What is the relationship between competing signals between your excipients and your API? There's other factors that go into considering whether you would be successful at 2 to 4%. I would say it runs into a lot of the same challenges that PLS does, but PLS has some specific advantages over IoT that make it a little bit more successful at those very low concentrations. So it's feasible in the right system, but I would not say it's a guarantee. I would start to have some real questions at that low of a concentration.
And I think the IoT approach is likely to be something for a future SentroConnect live event. One follow-up on that one, what about the moving block standard deviation comparison? Just one sentence maybe for very low API. If you compare similar, IoT versus that.
Yeah, similar story. You want to actually see if you can see that API signal. Doing wavelength selection to just focusing on the API peaks can be very helpful for moving block standard deviation when you're only concerned when you're having a low concentration of API. So that would be my advice in that particular derivative and wavelength selection.
Perfect. Good. We are at the end of the session officially, and we still want to answer the questions, but I think as people will typically also schedule their afternoons or their mornings, it's worthwhile to close now. With that, I'd say thank you to all of you for, on the one hand, the presentations, more importantly, to all the participants for your time, your interest, and also your questions. Keep in mind the videos will be uploaded to YouTube, so you will be able to enjoy this yet again. And of course, where there will be a follow-up meeting style event where the intention is to answer all of the remaining questions, and keep an eye out for the next events within the SentroConnect Live. We will continue with that. With that, thank you, everyone. There will be a short poll at the end. Maybe you will find the time to take this. See you soon.